Oh, welcome everybody to the Kaput Centre for our second talk this year in our new interdisciplinary colloquium series. It's a great honour and pleasure for me to introduce a friend and colleague, Nick Jackiw, who is the Chief Technology Officer of KCP Technologies and the software designer responsible for the Geometer Sketchpad, which is probably one of the most successful pieces of mathematics software, certainly in the States, but it has also sold millions of copies around the world, many parts of Asia as well. For example, Malaysia, you have a countrywide license, I understand, and it has just had an amazing impact and dissemination into the hands of teachers in many classrooms at many levels. As one of the founding members of the Visual Geometry project at Swarthmore College in 1987, Nick was responsible for the design and development of all of the interactive software that project was developing. In this capacity, he formulated the dynamic geometry approach that defines the Sketchpad experience. Moving with the software from an academic environment to the publishing industry, Nick has directed the Sketchpad product at Key Curriculum Press, which is a major curriculum developer that many schools, certainly local schools, use materials from Discovering Algebra and Geometry being two of those key texts. And he continues the project today at KCP Technologies with the ongoing support of the National Science Foundation. He's also an adjunct professor in the Faculty of Education at Simon Fraser University and works with schools around the world in conducting software field tests and evaluation. One thing that has always struck me, knowing Nick for quite a while, is the amount of energy that this man has, not just in his brilliant, innovative ideas, but his willingness to travel the four corners of the earth, working with people, teachers, and curriculum developers and faculty, hands-on. So he is here today, and it's a great pleasure to welcome Nick as he gives us a talk on perspectives on dynamic geometry. Thank you.
I'd like to thank Stephen and the Center for having me here today. This is really a personally meaningful opportunity. Jim was a tremendous mentor to me, as to so many, and it's a privilege to be here talking about my work in that context. So I want to talk about dynamic geometry, and before even getting into any sort of overview of my talk, I'd like to have us think together about a bit of dynamic geometry. And so I'm going to begin with a thought experiment that I'd like you to each participate in. And it involves some very rudimentary geometric construction. I'm going to build a circle and a radius of that circle and construct a point on that radius. So one of everything: a circle, a segment, and a point. And I'm going to ask you to think about how these objects relate to each other. And in particular, if I put labels on them and start moving C, which is defined to be a point on that segment, you can all see that the path of C, defined to be a point on that segment, is simply going to be that segment. There's nowhere C can go that's not on that segment by definition. But what's the path of C if I move A around the circle? What sort of locus is this describing as A moves around a circle? Circle. Looks like a circle. In a general configuration, if C were fixed on the radius and I was spinning it, I'd either have a circle or perhaps a point if C was here at the center. So those are two easy questions. Another question I want to ask you is, what's going to happen to C if I do both of those at the same time? So A is moving around the circle, C is moving on the segment. What shape is C creating? Like a flower. Like a flower. So do you see some petals that make you say that? C is generally tracing out these big lobed petals. How many petals are there once around the circle? More than 100?
No.
Less than 1?
It's like about 6.
About 6? Higher? Lower? Really, I'd like you each to have an answer to this question. You don't have to tell me what it is.
8.
Right, well this is
Maybe it's more like 3.
6, you're revising downwards, more like 3. This is the sort of question that we can answer very easily in Sketchpad just by tracing a point. So I'm going to trace C. And we'll see actually these petals now being traced out. So there's 1. There's 2. So already 6 looks too many. There's 3. And by the time it gets back up, we've got a little bit more than 3. Pi. All right? Now each and every one of you should know exactly why this is pi. There's only one number that's bigger than 3. It's pi. But more importantly, what you should understand is that a petal is what? A petal is the point going out the radius and back. So one petal is 2 radiuses. And my question is, how many 2 radiuses are in a circle? And we all know C equals 2 pi r. Right? So I like this as an example of Jim's big idea that he devoted a lot of time to in the 90s, that our mathematics is a function of and entirely dependent on the type of representations we use to express it. C equals 2 pi r as a bit of symbolism is something we all memorized in 6th grade, and many of us have taught again and again. And we have it in that form. But that's a statement about this. It's a statement about real circles and real radii. And when we see it in this context of the actual geometry, that symbolism is supposed to be describing, our knowledge of the symbolism doesn't transport to this encoding of the same proposition. All right, so the ideas, big ideas here are that our mathematics depends on the representations that we use, and that when we change the representations, that involves changing the mathematics. And that's frequently sort of misinterpreted in a trivial sense when we come to computers, in which people say, oh yes, now that I use computers, I can do new mathematics that I couldn't do, like fractals or iterations or some sort of computer-specific mathematics. But there's a much deeper sense that sort of our mathematical cognition is also functionally dependent on how we represent and encode the mathematics that we work with. And so in this talk, I'm taking the perspective that dynamic geometry is, in Jim's sense, a new type of representation and encoding of mathematics. And therefore, we should expect it to be deterministic of unique mathematical experiences and different in significant ways from prior mathematics experiences we've done. And I think this pi-petaled rose is a nice example of it. We'll just let this continue animating for a minute and probe it a bit more. Because unlike symbolism, the richness of the circle and radius relationship here is sort of evident in the whole, whereas with symbolism, in order to drive new symbolism, you need to permute and have your arithmetic and your algebra and your operations on symbolism. But if we're comfortable saying this was a pi-petaled rose, when will it repeat? Now I'm pushing you a bit further out of the box of just what's the formula. When will A come, or C come back to where it started? How many, it's pi one time around the circle. How many multiples of pi gives you a whole number? Now you see if I change the encoding of the question, it's beginning to map more clearly to the mathematics you understand. Okay, so it's never going to repeat.